All right, everyone, we have another example where we want to find the area between two curves. And this time we're asked to find the area of the region bounded by x equals y squared and x minus y equals 2. So our first step in our process is always graph our two curves and visualize our region. That'll help us decide how we want to set up our integral, whether we want to integrate with respect to x or with respect to y. Should we think of our region as being bounded on top and bottom or on right and left? All right, so our first curve or function that is given to us is x equals y squared. And this is going to give us a parabola. Normally we think of our quadratic equations and our parabolas as being described as y equals x squared. We have x equals y squared or something similar to that instead. Well, instead of our parabola being concave up or concave down, opening up or opening down, instead our parabola is going to open to the right or to the left. And with x equals y squared, we get a parabola that opens up to the right. So here is a visualization of our first curve, x equals y squared. And then we're going to have to graph alongside this our second curve, x minus y equals 2, which is just going to be a straight line, right? This is just a linear function. We might want to move things around a little bit and think of this as like y is equal to x minus 2. That might make graphing it a little bit easier. When we do graph our second curve or our line, we end up with this straight line in green, and that's x minus y equals 2. So now we can really see the region between our two curves is this little almost crescent region that I've shaded in green. So our next step towards making progress in this problem is deciding how do we want to set our integral up that describes the area between these two curves. Is going to be described with an integral with respect to x with a curve on top and a curve on bottom, or an integral with respect to y where we view our region as being bounded on the right and on the left. And with the picture we have drawn here, I think we can see and agree that our region is going to be most easily described with a curve on the right, our green curve given by our straight line, x minus y equals 2, and our curve on the left, which is given by x equals y squared. So we are going to be using our definite integral formula, the integral from c to d, curve on the right, which we'll call f of y, minus the curve on the left, which we'll denote as g of y, and we're going to integrate with respect to y here. And so our curve on the right is our green curve given by this linear function x minus y equals 2. But as we can see with this notation here, we have to describe this curve and its equation as a function of y. So that means we need to solve for x and express x in terms of just the variable y. And so we can add y to each side. And we see that x here is a function of y, where x is equal to y plus 2. So the first piece of our integral formula, our f of y function, is the quantity y plus 2. And now we're going to have to subtract away from that our left bounding curve, which is our other curve. Process of elimination makes that easy. And that's given by as a function of y as x is equal to y squared. Remember, we are integrating with respect to y here, and now to finish setting up our integral, we have to find the interval of y values that we go through in our region. So what is the lowest y value? Well, that's going to correspond to this point of intersection right here. And what is the highest y value obtained in our region? Well, that corresponds to our second point of intersection up there. Not all of our regions will have these nice points of intersection that finish creating the kind of edges of our region. But in those other scenarios, more information is given to us, which makes finding these kind of limit values much, much easier. And so now to find these y values, we have to find these 2 points of intersection between our two curves and figure out the y values of those points of intersection. So in our first curve is given by y plus 2. We want that to be equal to or intersect our second curve, which is y squared. And so now we have to solve this quadratic equation. Y plus 2 equals y squared. We probably want to rearrange that, put it in like your standard form. Y squared minus y minus 2 equals 0. And now it should be factorable. It'll factor as y plus 1 times y minus 2 is equal to 0. From that first factor, we see that y equals negative 1 will be one of our solutions. That corresponds to this lower point of intersection down here. And our second y value, that'll correspond to the one up here, and that'll be at positive 2. So now we know our limits of integration are from negative 1 to positive 2. So we have finished setting our definite integral up, and now we can evaluate it to find the area between our two curves. So not a whole lot to do when simplifying or rewriting our definite integral. We're still going from negative 1 to 2, and now our integrand is going to be the function y plus 2 minus y squared. So now we just have to evaluate this using the fundamental theorem of calculus. First step, or next step, is finding our antiderivatives. So all these antiderivatives are going to be found using our power rule for antiderivatives. The antiderivative of y, or y to the first, is going to be 1/2 y squared. The antiderivative of the constant 2 is going to be 2y. Remember, we're integrating with respect to y here and not x. And then our antiderivative for y squared is going to be 1/3 y cubed. So now we have to evaluate our antiderivative at the y value of 2. All right, so now if we plug in our upper limit of integration, our y value of 2, our first term in our antiderivative is going to be 1/2 of 2 squared. So 1/2 of 4 is 2. We add to that 2 times 2. So we add on to that 4. Then we subtract away from this 1/3 times 2 cubed, or 1/3 times 8, or 8/3. We have to also remember, we have to evaluate our antiderivative at that lower limit of integration at negative 1. When we plug negative 1 into our antiderivative, we end up with positive 1/2 for the first term, negative 1 for the second term, and positive 1/3 for that final term. Now we just take our first quantity, subtract away from it our second quantity, and our calculator can assist us in doing this, speeding that process up a little bit. But what we should end up with when we do this little computation is 9/2 or 4.5. So now we know the exact area bounded between our curves, x equals y squared and x minus y equals 2, is about 4.5, whatever those units happen to be. And so we are finished with this problem, but I just want to spend one more little minute talking about how we could have tried to attempt this the other way, and it actually could be done the other way, integrating with respect to x, but it's going to be a much more complicated problem. And what makes it more complicated if we're integrating with respect to x is that we'd have to use multiple integrals to describe our region. Because remember, when we're setting up everything with the integral with respect to x, we think of our region as being bounded by a curve on top and a curve on bottom. And well, the problem that we'd run into is that our top curve is going to be given by that function x equals y squared, but our bottom curve is also going to be given by that function x equals y squared, at least for this first little piece of our region. Once we move beyond this piece, once we're looking at kind of this, now I want to call it second half because it's not split perfectly in half, but this second piece of our region, well, then our top curve is still given by x equals y squared, although we'd have to solve that for y as a function of x. And now our bottom curve would be given by this linear function x minus y equals 2. So we don't want to go through that process because it's much more complicated, but if we did take the time to do that, we would get our exact same answer for our area of 9/2 or 4.5.